So my talk is going to be about hypervisor internals, the Microsoft Hyper-V slash Viridian stack, and some ways to communicate between partitions on the stack and to go from ring 0 using ring -1, as we like to call it, to talk between different partitions. So brief bio by myself. I'm currently chief architect at CrowdStrike, which is a security startup. Before that, I worked at Apple on the core platform team, and I was an intern there working on some of the basic OS functionality and porting that to ARM. I'm also co-author of the Windows internals books, 5th edition and 6th edition, and I've basically been reverse engineering Windows for the last 15 years, started with Windows 2000, and I've been doing that ever since. I started as the main kernel developer for ReactOS, and with that I basically did Windows internals training courses since then as well. So I like to speak at a lot of conferences, specifically targeting Windows design bugs and issues in new technologies that are coming out that are not necessarily related to buggy code, but rather buggy implementations or lack of foresight about certain combinations between certain types of techniques. So this talk is going to be about the Microsoft Hypervisor, which is often called Hyper-V, or known by its code name Viridian, which was introduced almost a decade ago. Now, originally, Viridian was only for server systems. It was a virtualization stack that you could run on Windows Server, but now, since Windows 8.1, it also ships on clients. So you could actually turn on Hyper-V client and run VMs inside of your client Windows OS as well. Now, Hyper-V is not used just for powering Windows, but Azure runs the Azure Hypervisor, which is also Viridian, and the Xbox One for security also uses the Hypervisor, which is also based on Hyper-V. So flaws in Hyper-V can technically, in most cases, also be flaws on the Xbox One or flaws on Azure. They're not exactly the same code, but they're very highly related. Now, very few internal details about Hyper-V have ever emerged. Ironically, some of the best documentation about Hyper-V worked was given at presentations by Microsoft at WinHEC in 2005, 2006, 2007. So if you Google for presentations from Brandon Baker or Marita, they talked a lot about the hypervisor internals back then because they were trying to convince people and companies that this was a secure hypervisor. There are some external researchers that looked at it. So someone in 2011 made a diff of a patch and found a DOS bug that way. And then a few researchers from ENRW found a flaw in 2013, and they presented it last year. And one of the good quotes from those guys was, any hypervisor is not a new security layer, it's a new place to find bugs. Now, there have been some talks about that, but no one has really talked about the interface to the hypervisor, how to talk to the hypervisor and how to basically use it as a platform inside of your own application or messing with it, not just fuzzing it for bugs. So in a decade, there's only been those two bugs against Hyper-V. So does that mean that there's no bugs in it, that Microsoft has written amazing code? I don't know, but I think it's more the case that people just haven't looked at Hyper-V in enough detail and people are not quite sure where to start. So I'm hoping that by the end of the presentation, you'll have some idea of what things to look like and how to start programming some code and messing with Hyper-V. Now, this talk is not about Azure 0 days. It's not about hypervisor rootkits. It's about basically empowering you to learn how to write hypervisor interface code and give you some direction as to how it works and interacting with it. Now, unfortunately, interacting with a hypervisor requires knowing some Windows driver development, and not just Windows driver development, but actually plug-and-play driver development. And plug-and-play driver development sucks. It's terrible. In fact, I barely know it. I had to learn it from scratch to even get something to work. And so we're going to have to talk about plug-and-play development, but it's okay because there's going to be lots of meme pictures, so hopefully that's going to make it less technical. And I'll also talk at the end about some interesting new changes in Hyper-V in Windows 10, which are going to make some of this stuff even more relevant, I think. So I'm going to try giving you a quick Hyper-V architecture in 10 minutes or less. We'll see if we can fit that in. So we'll talk about different kinds of hypervisors, the hypervisor architecture, what VM bus is, what VMWP is, what VSCs are. Talk about partitions, synthetic interrupt controllers, basically just enough to get you started to understand the rest of the talk. And then we'll move on to how to program with Hyper-V. So we'll talk about the documentation, the headers, the libraries, the hypercalls, the IPC ports, how you can actually talk to Hyper-V and talk between partitions. And since that does require some Windows driver development, I'll briefly talk about some of the challenges to actually get a plug-and-play driver up and running with this. And then I'll do a few demos. I'll show you a root partition talking to a child, and we'll see what that does. And I'll show you a child partition talking to a root partition. So we'll go both ways. All right, so let's start. Let's see if I can make this in 10 minutes, hypervisor architecture. So when we talk about hypervisors, virtualizations, there's two types of virtual machines we usually talk about, type 2 and type 1, and hybrids in between. So type 2 is like your .NET CLI or your Java VM. You have the host OS that's running a virtual machine process, and the virtual machine process runs some guest environments. Then you have the hybrids, which are basically you run an OS inside of a process on your OS. So that's like virtual PC, VMware, QEMU. We're basically just running another OS virtualized inside of your OS. And then you have the type 1 VMMs, which is basically the virtual machine running on the bare bones hardware, and then the host OS and the guest OS all run inside the hypervisor virtualization. And so that type of hypervisor is what Microsoft has implemented. So Hyper-V is basically loaded at boot, and in Windows 8 and later, there's a component called hvloader.exe on BIOS systems or hvloader.efi, and it loads one of two hypervisors depending on what CPU you have. So if you have an Intel processor, it's going to load HVIX64, and if you have an AMD processor, it's going to load HVAX64.exe. The hypervisor can be debugged, so you have the debugger library that's going to use, and then once the OS is up and running, there is a boot driver called hvservice.sys, which does some additional handoffs. Now, before Windows 8, there actually wasn't a hypervisor loader, so there was no hvloader.exe, and instead you had hvboot.sys, and it parsed the boot settings and then turned on the hypervisor. So in Windows 8, the bootloader actually turns on virtualization, and the whole OS process is then virtualized. In Windows 7, you boot it up in non-virtualized mode, and this driver took you in virtualized mode, and then basically kind of rebooted the machine in a soft reboot way. So now you're basically hypervised before even the kernel starts loading. It's done at the bootloader level. So in the Hyper-V language, we have what are called partitions. And each VM instance is called a partition. Now, the core virtualization stack, Hyper-V itself and the management and all of that stuff runs in what's called the root partition. And the root partition has full access to hardware. So right now, I'm actually running Hyper-V client. And right now, I'm on the root partition. This is where my normal OS is installed. This is where I'm playing games. This is where I'm using Visual Studio. I'm on the root. Then anytime I create a virtual machine, this creates a child partition. Now, child partitions and root partitions talk to the hypervisor kernel using what are called hypercalls. And hypercalls are like system calls, but they go from the kernel to the hypervisor. And what's interesting about these is that each hypercall has an access control list that determines which partitions can do this hypercall. So the root partition can do pretty much any hypercall at once. The children partitions are limited as to what hypercalls they can actually do. Now, a partition can either be a root partition, which is always going to be Windows, or an enlightened child partition, or an unenlightened child partition. And an enlightened partition basically means that you're running the hypervisor aware kernel or the hypervisor aware stack inside a child partition, and it's going to be emulated a little bit faster. So Linux and Windows have hypervisor support, and when you install Linux or Windows on a Hyper-V machine, the VMs are going to run a little bit faster than it would have because there's lots of calls to the hypervisor that are done through the hypercall infrastructure to tell it, hey, I'm going to wait on a spin lock. Don't waste time spinning the CPU. And then unenlightened child partitions are basically DOS or any third-party OS that doesn't communicate with the Hyper-V stack. So let's say you ran OS 10 under Hyper-V, which I'm not sure you can, but if you try doing that, then it would be an unenlightened partition. So basically, that's kind of a high-level picture from Microsoft, from TechNet, as to how the whole thing looks like. So your root partition is where you have the entire virtualization stack, and then you have your child partitions. Now, when the child partitions are enlightened, it means that they have what are called VSCs, and we'll talk about those. And VSCs are basically what emulate devices, and they can talk to something called the VM bus, which is the virtual management or the virtual machine bus. And the VM bus can talk to the root partition, which will then talk to the VSPs. So let's say you have a Windows or Linux device on a child, like a network card. Well, when the application tries to talk to the network card driver, it's actually going to talk to the network card VSC, which is basically going to make that I/O what we call an enlightened I/O. And it's going to go through the bus, to the hardware, on the VSP, and then it's going to be processed at that point. And the same thing for Linux, which has its own integration components as well. If you don't have an enlightened child partition, then you basically don't talk to VM bus, you don't have any hypervisor components, and at that point, any hardware access that you do has to be completely emulated the legacy way by the hypervisor. So we'll go back to this picture in a few moments because I have a few more kind of terms to discuss. Now, underneath all of these partitions, you have the hypervisor. And the hypervisor is basically a very thin microkernel that provides the hypercall interface, it provides a virtual processor scheduler, it provides a memory manager to kind of separate the addresses between different partitions, and it provides also interrupts support to emulate an APIC, essentially. So anytime you have a Hyper-V device, it's called a VDEV, or virtual device, and it's implemented as a pair. The VSC, which is on the child partition, it's called a Virtualization Service Consumer, and on the root partition, you have a VSP, or Virtualization Service Provider. And through the VM bus, the virtual machine bus, they talk to each other. Now, VM bus implements channels, and through the channels, the root partition can talk to any child that it wants, and the child partition can talk to any root partition that it wants. But child partitions cannot talk to each other. Now, these VSPs and VSCs are often called integration components or synthetic devices. So if you're on Linux, you'll be downloading what's called LIS, the Linux Integration Services, and that basically provides a bunch of Linux VSCs so that the Linux OS can talk to the hardware on the host by using the VSPs directly instead of having to emulate them. Now, for stuff like a serial port or floppy drive or an old BIOS-based network card, you don't have any of this, and instead it's done through the emulated fashion. So when the guest partition accesses an I/O port that's associated with the floppy drive, then the I/O port will be hooked, and then it will have to be emulated at that point. So that's the slow path. So on the fast path, again, these are your two partitions, and really, before your I/O request gets to the actual underlying hardware stack, there's going to be a filter that says, wait, let's not go to the real disk, because that's going to go to the hardware disk driver, and it's going to get emulated. Let's go to the VSC, go to the VM bus, bring it up to the VSP, and then the VSP on your host reissues the I/O again, and then it goes directly on the hardware. And with this mechanism, basically Hyper-V is able to, in almost all cases, transparently make I/Os go from the child to the host without having to do the normal emulation that's going to have to happen. So it's a very kind of efficient model behind that. But it does mean you have this component, VM bus, which clearly straddles among partitions, right? The partitions are fully isolated, but VM bus kind of exists in both. And that suggests there's an interesting attack surface there because obviously it breaks that boundary. Now there's also something called VID, and VID is the Virtualization Infrastructure Driver, and it basically connects the virtual management machine services with the Hyper-V kernel. So when you actually use Hyper-V Manager and you start a partition, stop a partition, resume a partition, add some memory, add devices, basically whenever you're using a Hyper-V UI, that UI is talking to the management service talks to VID, and VID talks to the kernel. So VID's basically kind of the management front end of Hyper-V. The back end is all done by the hypervisor. And there's a DLL called vid.dll, and it basically loads inside the hypervisor processes in user mode. It uses ioctls to talk to vid.sys, and then vid.sys talks to the hypervisor kernel by using hypercalls, and it manages that kind of stuff. It also manages the old style devices. So it provides MMIO emulation, and provides the BIOS ROM, the video ROM, so it also emulates some of the old DOS devices in case you're not booting an enlightened partition. Now in Hyper-V, CPUs are managed through what are called VPs, or virtual processor. And basically, what you see as a logical processor on your root partition can be shared among multiple children. So the scheduler basically decides the logical processor that's on your host, which virtual processor it's going to be associated with. And we call that a virtual processor, or VP. With Hyper-V, you can set up what are called intercepts. And intercepts allow you to be notified anytime there's an MSR access, anytime there's I/O port access, anytime there's an exception, anytime someone does CPU ID. And the intercepts are basically a programming layer around VTD or VTX. So instead of having to write your own hypervisor, if you have a machine that has Hyper-V installed, you can use intercepts to essentially build your own virtualization stack and receive notifications when any of these things happen. Now, VID is not documented, so normally you don't write applications that install intercepts. Normally the Hyper-V processes themselves install intercepts. So the Hyper-V worker process is going to have an intercept, for example, on the I/O port for floppy drives. And intercepts are used for synthetic devices or for exceptions or managing access to invalid memory. When an intercept happens, the partition freezes, the child partition freezes, it sends a message through a root partition, and the root partition decides what to do, and then we resume the virtual processor at that point. Now, memory in Hyper-V is separated into 3 types of memory, what we call GVAs, guest virtual addresses, and those are the virtual addresses in the child partition. And then you have GPAs, which are the physical addresses in the child partition. And then you have the SPAs, which are the real physical addresses inside the root partition. So you have a virtual address here that the local OS converts to a physical address, and then Hyper-V converts that physical address to the real physical address that actually exists. Now, as you probably know, with SLAT or nested page tables or EPT, we can also go directly from GVAs to SPAs, and the CPU knows how to do that with nested page tables. But the same idea is there. You have these separate layers of isolation between pages. Now, on the root, GPAs and SPAs are identical, because everything that's a physical address on the root partition is obviously a physical address on the root partition. And a GPA can either be mapped, which means there's a mapping between the GPA and the SPA. It can be unmapped, which means that it hasn't been used yet, it's not mapped, or inaccessible. And inaccessible is used when the hypervisor actually wants to protect even the root from being able to access certain things. In the original hypervisor, it was done for basic consistencies, because once you run the hypervisor, the interrupt controller is owned by the hypervisor, and we don't want the OS on the root partition to be able to mess with the APIC while the hypervisor is trying to touch it. But you could also technically use this mechanism for preventing even the root partition from being able to access certain hardware, which they hadn't done yet, but they may be changing some of that as well. Now, between all these GPAs and SPAs, there's what's called an overlay GPA, and the overlay GPA allows you to basically share a virtual page among multiple partitions, including the root. So an overlay GPA is basically a shared physical address that other partitions are going to see as well, and it's mapped to the same SPA. And this is what's going to be used when we do inter-process or inter-partition communication. Finally, the hypervisor has its own interrupt controller. So it takes your local APIC and it extends it by adding additional vector tables to it. And this is called the synthetic interrupt controller, or the SYN-IC. And the SYN-IC has 16 different local vector tables that are called SYNs. So you have SYN0, SYN1, all the way to SYN'15, and those are your 16 local interrupts that you can receive through the hypervisor. Now, these interrupts are sent either when the virtual processor writes to the APIC interrupt register, so when you do a software interrupt, or they can be generated when a physical device generates an interrupt, or when the hypervisor has some sort of tracing message or timer to send you. And the synthetic interrupt controller is also what's going to be used when we talk about inter-partition communication. So message flags, or event flags, sorry, I should say event flags, messages, and monitor notifications, those also involve the synthetic IC controller. So when you want to talk to the hypervisor, you use hypercalls. And the hypercalls are used for other management tasks, so being able to create a partition, suspending a partition, and so on. They're used for providing enlightenments, so optimizing TLB flushing or telling the hypervisor, please don't actually spin on the spin lock. They're used for IPC as well, which is how we're going to use them. And hypercalls can either be simple or repeat. So a simple hypercall is you're telling the hypervisor something and it does it right away. A repeat hypercall is something that's a little bit more complicated. And because it's more complicated, technically that means the hypervisor would stay in a locked state for a while trying to handle this call. So the way the repeat hypercalls go is every once in a while they're going to stop processing the hypercall, the VM's going to run some more code, and then it will come back and resume the hypercall. So it's kind of a continuation model where you don't spend the whole time in the hypervisor trying to do this call. And the idea is to reduce latencies. And there's 3 calling conventions that Microsoft documents. You can pass in arguments through registers, through a data structure, or through floating point vector registers. And all these things are going to be documented in something that I'm going to show you. Now, normally the hypercalls, they're implemented with a VM call instruction, and Intel does say that you can do a VM call from ring 3. But the Hyper-V stack doesn't let you do that. So if you do a VM call from ring 3, it's going to be caught in ring 0, and you're going to get an exception. So only the kernel and only drivers are allowed to do VM calls. A hypercall will then return a status value in RDX, RAX, and like I mentioned, due to latency constraints, the hypercalls have to return within 50 microseconds. If they don't, then you do a continuation, and that's what rep calls are used. Simple calls almost always come back within 50 microseconds, so you don't have this problem. Now, input and output has to fit in a single GPA address, and it has to be aligned correctly. And although hypercalls have to be done through assembly code, Microsoft provides an interface so you can do hypercalls from C code as well. So that's your quick hypervisor internals. So how do we program this thing? Well, one word of caution, this is an official quote when someone asked on the Microsoft forum, how do I program the hypervisor? The response was, there is no published way to do this and no support from Microsoft. If you try to do this, your system will most likely crash. So be warned, if you do any of this, according to Microsoft, your system will most likely crash. And this comes from the Hyper-V architect, so he probably knows what he's talking about. But when someone tells me there's no published way to do something, my first thought is, all right, let's figure out how to do this. So it turns out Hyper-V has actually excellent documentation from Microsoft. In fact, Hyper-V has better documentation than even the kernel. If you download something I'm going to show you, you get this beautiful doc that basically gives you every hypercall, and it tells you every parameter and the size. It tells you exactly what the function does in details. It shows you all the input parameters. It shows you all the output parameters, gives you the state restrictions, and documents every return value. If you've ever done Windows programming, especially kernel programming, and you're looking at a function and you got back status, some weird status from it, and you look at the Microsoft IMSDN and it says return values, status success, or appropriate status code. It's like, gee, thanks. They actually document every single one that is going to come there. So all this stuff comes in what's called the top-level functional specification. And you're not meant to read this. It's meant to show you this is just page 1 of the outline. And then the outline goes on for more pages. So it's an excellent doc, and you kind of have to read this before being able to do anything with the hypervisor. So the TLFS, the latest version, is called 4.0a. It covers Windows 8.1 and Server 2012 R2. And it not just describes the hypercalls, it also describes how virtual memory is handled, how scheduling works, how IPC works. It basically is a Windows internals for the hypervisor. And it's designed because Microsoft had to interoperate with other vendors, and this is how Linux can run under Hyper-V. So you can download it, the link is there, you can also just Google for it, and you're going to find it. Now the thing is, it's 410 pages. So I'm not going to tell you to come back tomorrow after you're done reading it, so we're kind of going to assume that I'll pre-explain some things for you. And in fact, the thing is so long, I often call it TLDR instead of TLFS, just because it takes too long to read. So you want to write some code. What do you need? You first need the Hypervisor Guest Development Kit, or the HVGDK, and you need the hypercall headers. The HVGDK is basically the internal development kit that takes the whole TLFS and condenses it into a header file. And WinHV.h takes all the hypercalls and makes them callable from C code by giving you a direct driver interface. Then if you want to talk to vid, you need vid.h and viddefs.h, which gives you access to the intercepts, the partition management, and all of that. And then finally, you need the import libraries so that you can actually link your code. So the Vista Windows Driver Kit actually ships with the HVGDK and with the HV headers. So they actually shipped everything you need to start writing code, except for vid. And the idea was, well, you don't need to talk to vid, or you shouldn't be talking to vid, because we don't want to document it. Now the problem is, if you don't talk to vid, you're not going to be notified, for example, if the user suspends a partition. And your driver code that thinks it's talking to the child partition out of nowhere will start failing because the partition has been suspended. And then if they resume another partition, then you get the same partition ID, and your driver talks to a new partition now instead of the old one. So all the kind of partition state management and suspend and resume is handled by vid, not the hypervisor. So one big caveat here is if you do talk to the hypervisor directly and you don't talk to vid, you will not be notified when these things are happening. So that's the warning from Microsoft, and that's my warning as well. But for just exploration purposes, as long as we never resume or suspend the VM, that should be good enough. Now, the problem is you get all the headers, but you don't get the library files. So some developer complained on Microsoft forums, this is pretty silly. You guys published the whole documentation, you guys published the whole header files, but you didn't provide us with the lib files. So we have to build our own lib files from scratch and do a bunch of hacks. Can you guys please fix this? And the lead hypervisor architect wrote, yep, I agree completely. We're going to fix this. The published interfaces will disappear in the next documentation. Since there's not anything you can do with them, we're just going to get rid of them since it won't help anyone. So basically, all the docs are still there, but all the headers are gone and all the interfaces are gone, and now the problem is gone because you can't talk to the hypervisor anymore. So you need to get that stuff back. Now you can get it back with something called Microsoft Singularity. What is Singularity? It's like not secret anymore, but it was a secret research operating system from Microsoft where they basically try to make everything .NET. Now, they ended up open sourcing Singularity, and they ended up open sourcing all of the headers that Singularity was using. And because Singularity could talk to the hypervisor, they open sourced all the hypervisor headers again. So, how do you get all the stuff? So to get the HVGDK, you can go on Singularity's Codeflex website, and you can actually get the vid headers as well, which are never officially published. So you get the hypervisor headers and the vid headers. This is becoming old, though, because Singularity is not worked on anymore. So if you get the LIS, the Linux Integration Services from Microsoft, you're going to have some header files there that pretty much cover everything you need as well. Now, you also need the WinHV headers, and those are not in Singularity because they're Windows-specific. But you can just find the old Vista Windows driver kit, and you'll get them. So if you have an MSDN subscription, it'll be there. Or if you know how to use Google, you can probably find these as well. And then you still need the winhv.lib. Well, you can create an empty definition file, print out all the exports in winhv.sys, dump them in a def file, and then recompile that or relink that with importlib, and you can generate an import library based on a definition file. And that works on x64 because the column convention on x64 doesn't have any decoration. So once you have a def file, some definitions in it, you can create your own import library. On x86, because there's naming conventions and SDE call and decorations, you have to create an empty C file. Inside of the C file, you have to actually write out every stub for every function. Then you compile that, and then you get an import library. But basically, because the exports are in the symbols, it's not terribly hard to do. Now, you have to be careful also because some of those headers come from Windows Vista. And in Windows 7, there's been some changes. One big change is that you no longer have a VMBus driver and a WinHV driver. You now have vmbus.sys and vmbusr.sys. And you have winhv.sys and winhvr.sys. So the ones with the R are the ones you're supposed to use on the root partition, R for root. The ones without an R are the ones you use on a child. So now you can't just have a driver that recognizes am I root or child and does the right thing, because you're going to be importing the APIs that have the same name from two separate libraries. So you actually have to build your own winhvr.lib and link a root driver linked against that, and a winhv.lib and link a child driver against that. On top of that, there's little changes that have happened over time in the WinHV interface. So for example, if you take the Windows Vista definitions that are public, well, in Windows 7, the port APIs added a NUMA node requirement parameter. So there's people online complaining that are trying to call the API and it crashes, and that's because of a new parameter. Or when I did this on Windows 10, the new, not the new, but the synthetic interrupt controller APIs, now they expect a group affinity instead of just an affinity. And so that structure is different, so it'll also crash. So no one's really maintaining those deprecated header files anymore, so you do have to open things up in IDA. But you have symbols, so it's not terribly hard to do that. All right, so how does IPC work, or inter-partition communication? You have three types of IPC mechanisms you can use. You can use what are called events, and events are basically a single bit flag. And every synthetic interrupt controller gets 2048 bit flags. 2048 bit flags covers 1/16 of what's called the synthetic interrupt event flag page. So you get a 4 kilobyte page. It's got 16 interrupt controllers, interrupt vectors on it, and each interrupt vector has 2048 bit flags. So you can send up to 2048 bits of information for a given interrupt vector. And obviously, you don't use this to package data. You use this to basically send interrupts or send little notifications to the root or to a child. And the sender signals an event, which is going to OR a bit. And if this bit is now on for the first time, then you're going to get an interrupt. If it's already on, then you don't get an interrupt. Messages, on the other hand, they're basically actual data. And you can send up to 256 bytes. And if you do the math again, 256 bytes times 16 vectors that are provided in an interrupt controller gives you 4 kilobytes. And we call that the SYM page, or the synthetic interrupt message page. And here a sender posts a message, which basically has a payload and a header, and this sends an interrupt to the partition. The partition then acknowledges the message, not by clearing a bit, but by either acknowledging the interrupt or by writing to a special end of message MSR. So you basically tell the root partition, or not, sorry, you tell the sender partition that you're done. If you don't tell the hypervisor that you're done, it'll resend the message a few milliseconds later. So you have to tell it if you're done, otherwise you're just going to get the message again, again, and again. The hypervisor guarantees message delivery within a single virtual processor. So if you're saying that there are 4 CPUs that can handle messages, and you have a sender that's sending messages, there's no guarantee that some CPU might not see this message and another CPU sees this message. However, if you only make one CPU available to the receiver, now you're guaranteed that all the messages that are going to be sent by the sender, they're all going to come in a queue. And VMBus, for example, uses that model to guarantee things. There's also what are called monitored notifications, but you can read the TLFS for that. We're not going to cover those. So, knowing this, how do you then create a port to actually start communicating? Because whether you're sending messages or events, you need a port. So a port, first of all, has to have a port ID. So you call WinHV allocate port ID. That gives you a port ID. Now that you have a port, you have to tell it, is it an event port or is it a message port? So in this case, we're doing an event port, and we're basically saying it's going to have flag 0 up to flag 32. So out of the 2048 bits, we're just going to use 32 of them. And we're going to send this to this interrupt vector. So you pick one of the interrupt vectors you've allocated. And we're going to send it to any virtual processor that we want. So we're not going to target these flags or these interrupts to a particular processor. Anyone on the other partition can receive them. You package all that in a port infrastructure, and then you call WinHV create port. You tell it who you are, or where you want to create this port, and who's going to be connecting to it. So you can create a port in a child partition, and basically this is the child, and you are the connecting root partition. Or you can say, I want to create a port in the root, and I want the child to be able to connect to me. So you decide who connects to who, and you pass it the port ID that you allocated earlier. And obviously, if this doesn't work, make sure you free the port ID, otherwise you're going to be leaking those allocated port IDs, and eventually you're going to run out of port IDs. So fairly simple process. Then you have to connect to a port. So the way you connect to the port, you basically tell it, what port are you connecting to? So that's, again, the same port you created earlier. What type of port is it? So this should match the port that you created. And then who is connecting to who? So in this case, we've got the child connecting to the root. So the root is the owner. The child is the connector side. And then you have to give it a connection ID to basically identify this connection. Now, the connection ID can be anything you want. So most people Microsoft people on the VMBus, they usually just set the connection ID equals to the port ID. So basically, your port ID and your connection ID are going to be the same. And now you have a connection. And once you have a connection, you can signal events or you can send messages. And what you're going to need is the connection ID on the other side. So it's not actually a lot of code once you can figure it out. So events, the way they work is you have the sender that basically flips a bit. And when the bit is flipped on that specific interrupt vector, the virtual processor, the receiver, gets an interrupt. You clear the bit once you're done. And at this point, if you get the interrupt again, it's going to come back. And you use HV signal event to send bits, basically. And you have to make sure here that you pass in the connection ID, and you pass in the bit number. And the bit number has to match what we set up earlier here. Because I said there's 32 flags starting at 0. So if someone tries to signal bit 38, they're going to not be able, they're going to get a failure code because it's not a valid bit that they can signal. So this is some very ugly code, but just to show you how an interrupt handler on the receiving side would handle the bits, you have to call another WinHV function called getSyncEventFlags. You give it your interrupt vector, and it gives you a page, or 2048 bits out of a page, which basically are your 2048 event flags. The event flags are separated into 32-bit U-longs, so you get 32 bits at a time, and you can then use bit scan forward to find out what is the first set bit. Now you know that one of those bits is set. You do something with that. Now we're not doing anything with it. Once you know the bit is set, you reset it, and you go back and you search for the next bit that's set. And this way you eventually find out all the bits that were sent to you as part of this interrupt, because maybe you got multiple bits sent by multiple partitions, and you just go over all of them. Once all the bits are cleared and you're done, you return from your interrupt routine, and now if other bits get set later on, you get the interrupt again. Remember, if you never clear the bits, it's like you never acknowledge the interrupt, and so if you get more signaling of the same bit, it's not going to wake you up again. So you have to clear the bits, otherwise you won't get interrupted again. With messages, you have a 256-byte message that you can send, or smaller. So you use HV post message to do that, and here you're passing in, again, the connection ID, and you pass in the payload size, and you pass in the buffer that you want to send. If you try to pass in more than 256 bytes, it's not going to work. So this goes in the interrupt message page, and the virtual processor, again, gets an interrupt at this point. So simple example on how you handle that. Same interrupt routine as earlier. You basically have to have the message page, and you get this again by calling winHV getSyncMessage page. This gives you the payload size, so you know how big the message is. It actually gives you the sender, so you know who the message came from. It gives you the port, so you know which port it was delivered. And it gives you the message type as well, which is something you can configure. So you can have different message IDs, message 1, message 2, message 3. In the example we're going to do in the demo, we're just sending a string. So we're converting the payload from a counted string to an ANSI string, and then we're going to print that on the debugger. Now, the thing you have to do now is to acknowledge that you received this message, because if you don't, the hypervisor might send it to you again. And the acknowledgement normally happens when we return true back to the OS. But by the time the OS actually acknowledges the interrupt, it might take too long. So what you can do, and this is written in the hypervisor specs, is you can override your message type to 0. And by doing that, you tell the hypervisor, actually, I'm down the message. And then if there's another message pending, you can actually tell the hypervisor, go ahead and send the interrupt right now by writing into the special MSR that's called the end of message interrupt. Because otherwise, you would return true, the OS would eventually complete the APIC signal, and then you'd get the interrupt. Once you do this, you get interrupted right away, and you can get a new message. So those are all optimizations to basically get messages flowing in as fast as you can, basically. So that's nice and easy code. There's just one problem. You have to register an interrupt with the OS. And if you try to Google or search how do you register an interrupt, there's basically pages and pages of information that say you just can't register an interrupt. Only hardware drivers can actually register interrupts. So then you have to know how to write a hardware driver. Now this is going to be really boring stuff, so we're going to try to make it more fun with really obscure anti-kernel jokes you're probably not going to understand to make it even more obscure. So when you write a Windows driver, there are two kinds of drivers, what are called legacy non-plug-and-play drivers, or kernel modules. And if you've ever written a driver, unless you work for a hardware company, that's probably what you've been writing. So security software, for example, rootkits, all those are legacy non-plug-and-play drivers. And then hardware plug-and-play drivers are called WDM drivers or WDF drivers. They are plug-and-play. Now, these both run in the kernel. They both run at ring 0, so you think they're kind of identical. But there's differences. Plug-and-play drivers will get certain I/O operations from the kernel's plug-and-play manager, and they have to respond to them. And we call those plug-and-play I/O request packets, or PERPs. Plug-and-play drivers get something called a bus enumerated device node. This is a special structure in the kernel that describes you as being a hardware device, and it ties you to a bus, and it ties you to a piece of hardware on that bus. Because you're tied to hardware, you can request, filter, translate resources. which means you can handle interrupts, you can do DMA, and you can access all the hardware states. And you get access to some kernel APIs as well. So it's kind of interesting because if you try to do any of these things without actually being a plug-and-play driver, in some cases, you're actually getting a blue screen of death. In fact, if you call any of these kernel APIs and you do not have a hardware plug-and-play driver, you get a blue screen of death. It doesn't even return an error, just crashes your machine, and basically says, a non-plug-and-play driver, try to call a plug-and-play API. And this is almost kind of like a patch guard level isolation that basically says, we don't want you to be doing DMA by talking to the Windows DMA interface. We don't want you to register an interrupt by talking to the interrupt interface. Because then how do we differentiate between a real interrupt and a fake interrupt? So you can go do sleazy stuff and talk to the DMA controller on your own, or you can hook interrupts if you want, but then PatchGuard can detect you. If you go through the normal mechanism, though, then you look totally legitimate. But to look totally legitimate, you have to have a hardware driver. So you want to start writing a hardware driver, you go on these internet forums and from Microsoft, and you go ask questions. And you have people that will basically tell you, why are you trying to do this? What's your end goal? Are you a hacker? And then they'll stop answering you. So there's a very famous guy, if you go on the Windows internals OSR archive, called Don Byrne, and he'll basically just tell you off and not help you. And I understand why, and I agree with it, because you don't want some random hacker figuring out how to do this, unless it's for good and research purposes, of course. So how do you become a plug-and-play driver? Well, the key to being a plug-and-play driver is you have to have a device node. How do you get a device node? Well, you have to what's called have a PDO, or physical device object. So how do you become a PDO? Because obviously the VM bus driver, which normally does hypervisor communications, you don't actually have a VM bus on your machine. So somehow it was able to get a PDO. So to get a PDO, you have to do a lot of work to basically get a software PDO, and that means writing an INF file and becoming a root bus enumerator driver. Like, I don't want to write INF files. I don't want to become a root bus enumerator driver. There must be other ways. So started searching the internet. And I find different people asking the same question, and the answer is always, make a root enumerated bus driver. How about using a root enumerated device? A root enumerated device is what you want. Write root enumerated virtual bus driver. Like, so then I'm like, okay, fine, I'll do that. I know how to write a Windows driver using WDM, the normal Windows driver model. And then I get emails and messages saying, use WDF. Write it in KMDF. Using WDM sucks. Don't waste your time with WDM. One solution is to use KMDF. Now, I don't know KMDF. I only know WDM. I'm not a hardware programmer, so I really don't want to learn KMDF. So I want to do this the WDM way. Well, the WDM way basically takes you back in time. Because if you think about it, back in NT4, they didn't really have plug and play. Back in the NT4 days, every driver scanned the bus on its own and then told the OS, here's my device, here are my resources, here's this and that. And then these APIs now, which still exist, they're all marked as deprecated, legacy, don't use this. But the problem is when Windows 2000 came out with this new way of doing things, with PDOs and plug and play, all the vendors hadn't gotten time to rewrite all their drivers. Some of them even went out of business. So Microsoft introduced an API that basically allowed you to remain an NT4-style driver, but get a PDO. And it turns out if you call IO reported detected device, you can tell the plug-and-play manager, hey, when you enumerated the bus, you missed me. I'm actually a PDO. And the plug-and-play manager says, okay, you're a PDO. You're good to go. So now you have a PDO, and you can call those APIs, and you can do all that stuff. Great. Well, not so fast. Because when you actually try to claim the type of interrupt that you need for the hypervisor, which is an APIC or MSI interrupt, not a legacy PIC interrupt, it's not going to let you do that. And if you try to request it manually with IO report resource for detection, it's going to write an undocumented flag in a structure, and it's not going to write some register key that's critical. And later, when ACPI tries to give you an interrupt, it's going to say, wait, hold on. This is not a real interrupt. You told me about this interrupt, which means you're a legacy driver. But I'm an APIC. How did a legacy driver from NT4 know what an APIC is? Those things didn't exist. You're lying to me. And basically, it's not going to let you have that. So you go back on the internet, back to searching for forum posts, back to listening to Don Byrne, and they all say, no, you need an INF file, or you need a root bus enumerated driver using KMDF. But I don't want to use an INF file. Because INF files are a pain to write, and they require user input, and I have to have an installer, and the user has to do a bunch of stuff. INF files are not going to cut it for me. So is there another way without an INF? Well, that's why I'm here. Turns out that if you use IO assigned resources, the really old API, combined with IO report detected device, and you plug in parameters the right way, and you work out this gigantic structure that's like code you probably don't want to understand right now, it lets you basically claim an interrupt as a legacy interrupt, but using the API that makes the plug-and-play manager think it actually found this interrupt. And so you basically get to claim the MSI interrupt, and then you get the interrupt, and then you can actually connect to it, and everything works out fine. Well, actually it doesn't. Because once you claim the interrupt any source, you get what's called an untranslated interrupt. Because back in the day in old hardware devices, you had what the bus saw as the interrupt or the memory address, and you had what the device saw as the memory address or the bus interface. So you had a translation interface that took your device saying, I want interrupt 28, and then the bus translator and the bus arbitrator converted that into what the interrupt number actually is. And when you assign resources to yourself, you're assigning what you think the resource is, and you have to get the resource translated, and then the translation is what you can register. Now, in most modern systems, the translation doesn't really do anything, because what the bus sees and what the device sees is the same thing, but you have to get to that translation stage. How do you get a translated resources? Well, the plug-and-play manager gives them to you. It sends you a special perp called the IRP MN start device, and you get back as input your translated resources. But the fake PDO we just created, it doesn't get IRP MN start device until you reboot. So again, it makes this whole exercise useless. So I've tried every possible way I could think of to get an IRP MN start device. But no matter what I tried, I had to reboot. So I was almost giving up. So I found a blog post by one of the key plug-and-play people at Microsoft that basically wrote a blog post on how to test plug-and-play changes. What if you're writing a driver and you want to get a start device? Or what if you're writing a driver and you want to get a stop device? I'm like, hey, that's exactly what I need. And it turns out there actually was a way. You had to call IO invalidate device state. This gives you a special perp called query PNP device state. And then you follow the blog post, and it tells you, if you want this, you need to specify this. I'm like, woo. So people have questions.
Does anyone have questions for Alex? They just want to see your demo.
All right. And here we go. So meanwhile, I'm going to start my little driver loader. So on the server side. Side. All right, so first I'll start up the server side, hope it works. All right, I have to clean up. After, one of the annoying things about this is that you end up with all this stuff if you don't clean up after yourself. Don't have to get rid of all of them. There we go. All right, so load it again. All right. So that's just my driver chatting on the, let's make this a little bit bigger, consolas. So basically that's the driver receiving all the information. Start OK. It received one interrupt, an MSI, PCI3 interrupt, and we got vector 72 from the operating system, and we're running on interrupt vector 6. And on interrupt vector 6, this is our message page. So this is where the hypervisor is going to give us messages. This is the interrupt vector on which we're going to receive messages at the hypervisor level. And this is the OS interrupt vector where we're going to be receiving interrupts at the kind of root level. In fact, if I open up a local WinBag now, do a bang IDT72, there's my driver loaded in the interrupt dispatch table. So I have a software driver that was able to claim a K interrupt. So this is OS stuff. So let's see if the client loads on the client side. Register and run. The operation could not be completed. A retry should be performed. All right. Demagogues are not with us. Let's see if we can give that one more try. Give it a quick recompile. Open project, Hyper-V. Their prayers, my prayers have not worked out. Well, we've got half of it working. We'll see if we get the other half. All right, hit the client. I think I know what's going on. If zero out this stuff, if zero out this stuff. I was playing around with some things and forgot to clean them up. And then re-enable this stuff. And kill this. Recompile. Oh, one more thing to get rid of. So here we're going to be sending message hello, 5 bytes, message type 1. Compiled. Get rid of this one. All this excitement for just a hello world. x64. Wrong directory. x64. Where is it going? See where the path is. Too many projects. So that's our client. All right, plug it back in, replace, replace, replace. Cross fingers, sacrifice the goat, and register, and so it does come back. So that's child talking to root. Now, let's just do the other way around. Send a message to the child. That's going to be a lot faster. And this time I said, well, instead of basically sending my own interrupt and sending my own channel, why don't I just try talking to VM bus? just for the hell of it. So this is me sending a message to VMBus, because I was playing around and fooling around with it, basically. So I'm going to attach a debugger on the client side, just so you can see the messages. And pick a different driver this time. All right, so client is good to go. And this time I want, let's see the name. I want this guy, hyper server. Rebuild. Register and run. So that's what happens when you run my little app, because I made a little mistake. It crashes in VMBus, referencing memory at 3, whoops. It's a null pointer deref, basically. It does R14 plus 348, and 348 is the address. So if I let it go, what you end up with is a beautiful blue screen of death. And this is not my driver doing this. This is Windows doing this. So basically, while screwing around and making a bug in my code, I ended up crashing Hyper-V. So by accident, I ended up discovering a bug in it. So not only can you talk between partitions, but it turns out you can also crash partitions. So that's an example of using the hypervisor to do nasty things. Now in this example, we went from parent to child, so maybe it's not really a big deal, but still fairly interesting. And all I had to do was basically screw up my own code. Instead of sending an interrupt to what I thought I was sending an interrupt to, I picked the wrong interrupt vector, and it turns out that VMBus doesn't expect you know how to talk VMBus. It's one of those, oh, if you can talk my protocol, I trust you. And basically it crashes because I send an interrupt flag that it doesn't expect. It dereferences that in its array of interrupt objects, and it gets back a null. So instead of having a crash, I could have actually had an application on a child that registers something a null, and I could have gotten code execution that way as well. So I think it's a lot of interesting things to play around with there. On top of that, the overlay pages, the pages that actually contain the data that gets passed across the event flags and the messages, they're actually allocated as executable. So the hypervisor actually allocates data pages as executable pages, and that can significantly increase attack vectors. Now, I told a friend at Microsoft about this about 2 months ago, and out of nowhere, suddenly in the latest Windows 10 builds, they're no longer executable. So I don't know if that's a coincidence, or maybe you shouldn't be telling your Microsoft friends bugs that you find. There's also no real validation of port IDs. There's a lot of trust that if you know how to speak to this interface, you must be legitimate. So you can actually free ports that are still in use, and you can actually free ports more than the number of times they're allocated, and then you can unsign overflow, and now you have like 80,000 ports allocated. So you get lots of weird behaviors if you poke at the hypervisor in place where it doesn't think you can poke at. And then in typical Microsoft fashion, even though all the hypercalls are documented in that giant 400-page book, there's actually undocumented hypercalls as well. Hypercalls to dump memory, hypercalls to actually turn off the hypervisor and keep your machine running, which is fairly interesting. And so if you reverse engineer the hypervisor, you can see these additional system calls that are not documented. And if they're not documented, perhaps you're really not supposed to call them. So who knows what would happen if you called them. Now, the last thing I want to close up with is that in Windows 10, there's going to be significant increased use of the hypervisor. One of the things that Microsoft is doing, and some of you may have saw me tweet about this, is something called VSM or VTL, which will basically introduce a secure kernel mode environment and an isolated user mode environment. And you're essentially going to have your root partition, ring 0, be protected against another root 0 partition, which is going to be called the secure kernel. And now, even though you're running on the root partition as root as ring 0, you won't be able to get to the other side where the secure kernel is. And a secure kernel on the other side implements an isolated user mode, which you can't get to from your user mode, and you can't even get to from your kernel mode. And what they're going to run in this isolated user mode is LSAS, which controls the password hashes and the clear text credentials. And all of this is basically to prevent pass the hash attacks, Because now if you run Mimikatz here, it doesn't see the hashes anymore. If Mimikatz loads its driver, even the driver can't see the hashes anymore. All of this, though, relies on the channel here being safe and the hypervisor being safe. So vulnerabilities in a hypervisor at a bus could now technically allow you to do this kind of jump as well. So Windows 10, they're now going to use this to actually enforce OS-level security. There's also rumors about drawbridge or Docker-type applications being virtualized on the same OS. So there's something called the Pico process in Windows 10 and Chambers. And there's all these internal research projects at Microsoft to basically use Hyper-V to define new OS boundaries. And if all these boundaries are relying on this one thing that no one's really looked at, I would certainly submit there's a lot of interesting stuff to look at there. So next year, the next SyScan 2016, I'm going to submit a talk and talk about secure processes and Pico processes. So I hope you're all going to come there. And I also got an email from Frack asking me to write an article for them, because Frack's coming back apparently. So I'll publish a full white paper detailing exactly how we did all this with code samples and all of that when Frack publishes that. So I think that's it. Any questions?
Thank you, Alex. Can you bring the mic to him? Bring the mic to him. Behind you. Malvis, hold on. About the feedback form, there's one question asking you what you want to see for next year's SyScan. You don't have to answer that question. That was an old template, all right? Yes, Malvis.
Great presentation, thank you. So do you need the fake device driver on both the root and the guest, or just one of them?
To actually just, like the crashing message I sent, so if you just want to talk to VMBus, you don't need anything fake at all, because VMBus already does it for you. If you want to build your own kind of local bus, you need a fake on both sides if you want to do bidirectional. So if you just want to talk to one side, you don't need a fake driver on the other side. But if you want to do both, you need both.
Anyone else?
Just to clarify that then, with your driver loaded in the guest, there's a multitude of other ports and stuff that you can talk on at the root level, right?
Yeah.
And that's where the crashes are going to be?
Yes.
Yeah. Thank you.
Anyone else? No? Okay. Thank you, Alex.
Thank you.
Thank you very much.